Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on October 22nd, 2025, which was about 2 days ago. Its key move is a selective, representation-centric survey that shows how to choose 4D representations for geometry, motion, and interaction by weighing fidelity, controllability, compute cost, and task fit. The paper is titled, Advances in 4D Representation, Geometry, Motion, and Interaction, and as we will see, the guidance for picking the right tools is quite practical. Beyond the taxonomy, this paper highlights hybrid models that mix structure with neural residuals, 4D native Gaussian approaches, the growing role of large language models and video foundation models, and the persistent data bottlenecks shaping progress. Alright, the introduction framed geometry, motion, and interaction as the three pillars. Figure 1 presents representative applications that map to each pillar. The top left shows mesh animation as a geometry task, while the top right shows dynamic point map reconstruction. The middle row illustrates motion, with 4D in betweening on the left and 4D semantic segmentation on the right, which tracks categories over time. The bottom row focuses on interaction, contrasting human-scene interaction and human-object interaction. So the previous figure sketched applications across geometry, motion, and interaction. Figure 2 contrasts 7 geometric representations for 4D content, spanning mesh, point cloud, Gaussian splatting, NeRF, template, part, and graph. Meshes deliver crisp surfaces and fast rendering, while point clouds tolerate topology changes. Gaussian splatting supports real-time differentiable rendering, and NeRF captures rich appearance but often flickers over time. Templates and parts add controllability for editing, and graphs encode relationships that matter for interaction. Well, Figure 3 organizes the field into a single taxonomy that traces 4D representation across geometry, motion, and interaction. The top branch maps geometry, splitting structured and unstructured choices, which helps clarify when templates, parts, or graphs offer control versus meshes, point clouds, NeRF, or Gaussian splatting for fidelity. The center stream details motion with articulation, deformation, and tracking, so methods can pair kinematics with learned residuals. On the left, the interaction branch groups action, affordance, pose, contact, and physics to support controllable multi-entity scenes. Alright, the previous figure organized the taxonomy across geometry, motion, and interaction. Figure 4 shows how motion gets attached to geometry across representative panels. The left panels illustrate articulated motion, where kinematic parts drive objects like drawers and desk lamps. The center panels present deformation and tracking, in which a deformation field warps a template, and time-varying trajectories control Gaussian attributes. The right panels depict hybrid schemes that mix rigid bodies with non-rigid cloth to capture garment and human deformation. So the previous figure tied motion to geometry across several schemes. Figure 5 presents interaction-specific representations, which span pose, contact, affordance, and physical properties. Panel A encodes poses between entities, using learned descriptors that remain consistent across scenes. Panel B visualizes contact over time, highlighting where the body touches floor, sofa, or table. Panel C depicts affordances, showing actions like grasp, pour, or cut that objects invite. Panel D models physics, estimating forces and resistances, so interactions remain plausible. So the previous figure highlighted interaction primitives. Table 1 summarizes representative 4D methods across 4 axes, which are geometry, motion type, input condition, and training strategy. The geometry column spans mesh, point cloud, NeRF, Gaussian primitive, template, part, and graph. Motion labels cover articulation, deformation field, tracking, spacetime, and per frame. A clear trend emerges. Gaussian primitives dominate dynamic rendering, structured templates and parts enable controllability, and per-scene training remains common while hybrid schemes grow. So the previous table profiled methods by inputs and training. Table 2 compares 7 representations across 7 dimensions, so it highlights where strengths and gaps lie. NeRF and Gaussian splatting deliver very high visual fidelity with high scalability, yet they only reach medium temporal consistency. Point cloud excels in scalability and efficiency, but suffers low temporal consistency. Mesh stays consistent but fixes topology and remains low in efficiency. Structured choices like graph, part, and template achieve very high consistency and editability, while generalization stays excellent within category. Wrapping up, 2 takeaways stand out. Representation choice must follow the task, balancing fidelity, temporal consistency, editability, and compute, And hybrid schemes that pair structured control with neural residual detail are emerging as the sweet spot. The broader push is clear. Better data, cross-representation conversion, and physics and interaction-aware models, guided by large language and video foundation priors. Thanks for tuning in to the AI Research Roundup. I am Alex. Thanks for listening.